Hey there, Math 120 fans. Sadly, this will be my last of my Exam 1 topic videos. This is going to be about quadratic modeling optimization. I absolutely love optimization. I think these problems really illustrate a fundamental idea and an idea that will continue on into calculus. Okay, so the way you do these calculus problems is exactly the same. It's just if it's a quadratic, we can do it. If the problem leads to a non-quadratic, we can't. Okay, so here's the question. Danny has 950 feet of fencing to make a rectangular enclosure with two parallel fences that divide the enclosure. What dimensions will maximize the total area? Here's how these go. You're going to label and draw a picture. Then you're going to ask, what does the problem want? And then you're going to figure out what is given. You will use what is given to get a one variable function, hope that it's a quadratic, and find the vertex. Of course, you'll need to interpret. So I'm going to label. I don't know, for something like this, I kind of feel like I'd like to label these little pieces. I don't know. Let's label the whole thing. Let's label this X. You can see I'm not that worried. That's X, that's Y, that's Y, that's Y, that's Y. And then the area of that entire thing is just X times Y. Right, so what about these pieces in the middle? Assume they're very thin. You're just trying to find the total area. So the total area is one big rectangle. X times Y. Okay, so those are our starting pieces. I've labeled everything, done. What does the question want? What dimensions will maximize area? So we want dimensions, but this is all about area. So we're trying to find when we have max area. In math, we call it the objective. That's the thing we're going to find the function for. So in a moment, we're going to find a one variable function for area. We're going to hope that it's a quadratic, and then we'll interpret and hopefully be done. So that's the layout of these problems. If it's not a quadratic, we can't do it. Then you need calculus. Okay, what was given? We were given this constraint, we say. 950 feet of fence. So all the fencing has to add up to 950. Well, there's 2 of length X, there's 4 of length Y, that's 950. I often say that these questions don't make sense without a constraint, because if the question said, I want the area to be as big as possible, you just make it as large as you want. You would just make X 1 billion and Y 5 trillion or whatever. You can keep going bigger. But these are constrained. They're constrained by the fact that 2X plus 4Y has to be 950. So here's how we finish. We solve for our variable. One of the variables, it doesn't matter which one. We divide by 4, so let's do, got my calculator ready, 950 over 4, 237.5, minus a half X, because of 2 divided by, okay. We take that and say that's the relationship. So if I want the area subject to this constraint, is how we, fancy way to say it, it's this. Then we expand. And then we're essentially done. We've accomplished what we want. We have a one variable function. That one variable function represents the area. That's it. So you could do, sometimes students tell me they have to come to office hours and we do a bunch of examples where I plug in numbers. We could say if X were 100 feet, then you could figure out what Y is and then figure out what the area is. But that's the same thing this formula does. Now we want to know what X makes this formula the biggest. This is a sad parabola, so it's the vertex. X is negative B over 2 times A. So it's 237.5 feet. And then from that, you can figure out y, plug that in here, and that's it. So the big takeaways here are realize that what your objective is. This is the thing that you're hoping is a quadratic. Take what you're given to turn it into a one variable function. Let's see another one. Bill sells liters of juice using a sliding price scale. If he sells 4 liters, then the price is $7.50 and his sale is this. Okay, so I got to think about that for just a second. Oh, this times that. Let's see if we are understanding. 4 times $7.50. Oh, he's going to get $30. So this number is just the product of those two. You sell 4 liters. Okay. And he's offering a discount. It's a little bit less if you buy 8 liters, but if that convinces people to buy it, more money comes in. So times 8, $54 comes in. Okay, that's that idea. And then it says price per liter is a linear function. What's that about? So why is this here? So the moment you see this, you should be saying, okay, it's telling me something is a line. But the something it's talking about is the price per liter, that number. Okay, so I do have some data points for this. That when x is 4, it's $7.50. And when x is 8, it's $6.75. So we can find the equation of that line. Let's do it. $7.50 minus $6.75 over 4 minus 8. So let's do it. $7.50 minus $6.75 divided by -4. Okay, so the slope is negative 0.1875. So now I have the price. The price is given by this, negative 0.1875 x minus, we pick one of the values, how about the 4, plus 750. That's what we're given. But it's not what we want. What we want is maximum sale. Maximum revenue, I would say. So how do we do that? Well, what is the amount of money he gets? What's the revenue? What's the total sale? So the revenue is x times y. X being the number of liters, y being the price. This is just like the previous problem. So I'm going to expand this out and simplify it. So let's do that number times negative 4.75. This is going to be negative 0.1875x plus 0.75 plus 7.50, and we've done it. And it happens to be a quadratic. So we can expand all this out. I think that together is 8 1/4. And then we can find the vertex. It's the sad parabola, the x-coordinate of the vertex, negative b over 2a. So I'm just trying to give you a few. I'm not doing every detail. I'm doing quite a few details, but not every detail of these problems because I want to see a few of them. Over 2a. Hooray, done. And do let me know in the comments if you find some typo or something. You can also check the solutions. These are all problems from my practice sheet. Let's keep going. Kramer has an apple orchard. One season, his 200 trees yields 100 apples per tree, which gives a production of 20,000 apples. He has a limited number of space. For every 10 additional apples, he will lose 6 apples per tree. It says use a linear model. What's that about? Oh, it's the same sort of thing. These two things multiplied together. So this is just like the last problem. So here's what we're going to do. Apples per tree. And they told me a few data points. They said when x is 20, this is 100. They also just told me the slope almost exactly. Every time you have 10 more trees, you lose 6 apples per tree. You don't have to think through it like I just did. You could also just, if you would prefer numbers, you could have said, well, they told me what 200 trees does. So if I add additional, so that's going to be 210, then this is going to be 96. So you could have used those 2 points to find the equation of the line as well. So negative 0.6 x minus 200 plus 100. I would then simplify that, and then I would do x times y. X is the trees. Y is the apples per tree. And I think I would probably do negative 0.6 times 200. What's going to end up being positive 120. So I think this is going to be negative 0.6x plus 120, so plus 220. Expand it out. So that's your function that represents this next part, production. It's happens to be a quadratic. Has to be, or else we can't do it in this course. Find the vertex and you're done. So I'm kind of skipping around. I'm doing the main themes. Part A was just to find the linear model, so you would have stopped here. But this is what you do in part B. All right, let's keep going. Another area question. What do we want? Maximum total area. What are we given? 400 feet of fence. So let's do it. So we want the area to be maximum, and the area is x times y. We're given the following, that the fence all adds up to 400. Looks like there's 1, 2, 3, 4, 5 y's this time. And there's 2 x's, and that's 400. Solve for one of your variables, x or y. I'll solve for y just to be consistent. Divide. It's going to be 80 minus 2/5 x. Substitute, that'll give you a one variable function for your area. Find the vertex, done. Starting to get a feel for that. Here's another one. What do we want? Maximum possible total area. Now this time it's a different shape, but what does it tell me? It's the shape of a rectangle, so let's call this x. The perimeter is 100 with a quarter circle top. I think I would want to label this y. That's just my, I don't know, maybe I should label the whole thing, but this is this radius. So that means this is also x. So that's a little tricky about how to label. There's other ways, other correct ways to label it. But the area of that is going to be x times y plus the area of this quarter circle, which is 1/4 pi r squared. R is x. So that's a little more involved area formula. What's my constraint? My constraint is the perimeter is 100. This is probably more of a question I would ask later because we haven't really talked about perimeter of a circle. I'm worried students wouldn't know it. So I'd give some hints. I guess if this appeared on a test, but the perimeter all the way around of a circle is 2 pi r. So a quarter of a circle is 1/4 of that, which is going to end up being 1/2 pi r. So what they were telling me here is that the total perimeter of all this, which would be x plus x, so 2x, plus 2y, plus this outer edge, which is 1/2 pi x, that has to be 100. We're going to solve for y, substitute in, that'll give us a quadratic, we'll find the vertex. So we get 2y is equal to 100 minus 2x. Sometimes when there's a pi, that throws people off. Divide everything by 2. Shove this in here, expand everything out. That's a quadratic. Find the vertex and interpret. One last one I thought. This is actually uniform linear motion. I'm going to skip the description and just say, assume we've already done this. These are their 2 coordinates. This was the answer to part A, Albert's coordinates, and this was Betsy's coordinates. And the question says, when will they be closest together? Now that's a minimum. What we want is a minimum distance. Now the distance between them is the following thing. So it's going to be x minus x. So that's what we're going to put here. Negative 3 plus 6t minus 2.5t. And y minus y. So that's what we're going to put here. 4 minus 2. This should be a plus here. I don't know why I did that. Minus 5 minus 0.25t. That's it. That already has everything we want in there. But this whole thing can be simplified pretty dramatically. So we have negative 3 plus 3.5t squared. And we have negative 1 minus 2.25t squared. This under here is a quadratic. If you expand all those out and can get it in the form a, b, c, then you can find the vertex of that. And that will tell you the t value when that is smallest. It turns out that the square root being around it doesn't change when it's the smallest. All right, so there's a sampling of those questions. We'll do more in class. But key things are, what do you want? What are you maximizing? What are you given? Find the vertex.